In continuation of this holiday special thing I have going on right now, where I'm releasing a video every day, we have this really cool integral. It's the integral from 0 to infinity of x times the cosine of x divided by e to the x minus 1 dx. So yeah, it looks really cool, and we're definitely going to have a really awesome solution development and final result. So let's get started by getting rid of the cosine term. And I can do that by invoking Euler's beautiful formula. We know that cosine x is the real part of e to the ix, which means that my integral I is the real part of the integral from 0 to infinity of x times e to the ix divided by e to the x minus 1 dx. And this thing absolutely screams geometric series. But right now, the arrangement does not give us a convergence series on this interval from 0 to infinity. So we can fix that by expanding using e to the negative x. That gives me I equal to the real part of the integral from 0 to infinity of x times e to the, on multiplying the two exponentials and factoring out a negative x, I have 1 minus I divided by 1 minus e to the negative x dx. And now we can use that geometric series arrangement I was talking about. Recall that the reciprocal of 1 minus x can be expanded as the sum over the non-negative integers k, x to the k, provided that the absolute value of x is less than 1. And in this case, we have 1 by 1 minus e to the negative x, and e to the negative x is less than 1 on this interval of integration we have. So we have the sum over k of e to the negative kx. And all of this implies that my target integral I is the real part of the integral from 0 to infinity of x times e to the negative x times 1 minus I times the sum over k of e to the negative kx integration with respect to x. And because these two are independent of the index variable k, we can slip them inside the summation operator, and we now have the real part of the integral from 0 to infinity of the sum over k of x times e to the, again on multiplying the two exponential terms, we have negative x factored out, and we're left with k plus 1 minus I, and we have this integration with respect to x. From here we can switch up the integration and summation operators, because this damping factor of e to the negative x guarantees convergence. So we have the real part of now the sum over k of the integrals from 0 to infinity of x times e to the negative x times k plus 1 minus I dx. And the structure you have is a really cool one now, because this thing that I'm just boxing up in blue is the Laplace transform of x when the variable s equals k plus 1 minus I, which is pretty cool. Now, the Laplace transform of x to the n equals gamma n plus 1 divided by s to the n plus 1. So in this case, we have s equal to k plus 1 minus I. So all of this means the integral I is the real part of the sum over k of gamma n. Now, the exponent on the x term here is 1, so we have gamma 2, terribly sorry about that, divided by the value of s here is k plus 1 minus I. And again, this is squared. And gamma 2 is just 1 factorial, which is 1. So this is what we have. We can now expand the square in the denominator, and we have the real part of the sum over k. But wait, what if I make a slight change going from k plus 1 to k? Now I have the sum over the positive integers k of 1 by k minus I squared. Now to expand the square, we have the real part of the sum over k of 1 by k squared plus I squared minus 2ik, and I squared is of course negative 1. And to separate into real and imaginary parts, I need to expand using the conjugate. So I'll expand using k squared minus 1 plus 2ik. And here we have the same thing downstairs, which implies that I is the real part of the sum over k of k squared minus 1 plus 2ik divided by k squared minus 1 squared. And we have this plus 4k squared term. Okay, cool. And we can still work a bit with the denominator here. We have a real part, sum over k squared. Wait, the real part is just going to be with the k squared minus 1 in the numerator. And in the denominator, we have k to the 4th power plus 1 minus 2k squared plus 4k squared. And that, of course, gives me plus 2k squared, which means I finally can write the sum over k of k squared minus 1 divided by k squared plus 1 whole thing squared. And what we need now is a quick partial fraction decomposition that I'm just going to write out because, well, it's trivial. We have the sum over k of 1 by k squared plus 1 minus 2 divided by k squared plus 1 squared. Okay, so I have two infinite series now. One is the sum over the positive integers k of 1 by k squared plus 1 minus twice the sum over k again of 1 by k squared plus 1 squared. So how exactly do we deal with these infinite series? Well, I made a video a few days ago where I evaluated the sum over k of 1 by k squared plus x squared using residues, link in the description below. And this infinite series sorted out to pi times x times the hyperbolic cotangent of pi x minus 1 divided by 2x squared. So for the first series, I'll call this s sub 1. For s sub 1, I just need to plug in x equal to 1, meaning that s sub 1 would be pi times hyperbolic cotangent of pi minus 1 divided by 2. But what about the series that I'm now calling s sub 2? That kind of brace is really hard to draw. Anyway, so what about s sub 2? Well, s sub 2 has k squared plus 1 squared in the denominator. So if I had a series that had k squared plus x squared squared, that would be quite helpful. And that's not even a problem. All I have to do is differentiate the whole thing with respect to x. Okay, so this implies that I have the sum over k of now k squared plus x squared squared in the denominator, a negative sign, and I have a 2x term because of the chain rule. And on the right, I need to differentiate with respect to x pi x times hyperbolic cotangent of pi x minus 1 divided by 2x squared, for which I need the quotient and the product rules for differentiation. Been quite a while since we used one of those things, right? I mean, all we do here are integrals and differential equations. I mean, the only time I ever use differentiation on the channel is to come up with an infinite series expansion or to differentiate under the integral sign for Feynman's trick. Yeah. Anyway, so we have 2x squared. Now the product rule, pi times hyperbolic cotangent pi x plus pi squared x minus sign because I have the squared hyperbolic cosecant thingy. Okay, derivative of 1 is 0 because 1 is a constant. I'm sure that's a well-known fact. And I have this plus, no, it's a minus sign. Pi times x times hyperbolic cotangent pi x minus 1 times 4x, correct? Okay, all of this needs to be divided by 4x squared. And I need to plug in x equal to 1. So x equals 1 gives me the sum over k of negative 2 divided by k squared plus 1 squared. equal to 2 times pi times hyperbolic cotangent of pi minus pi squared times hyperbolic cosecant squared pi minus, what else? Oh yeah, minus 4 times the pi times the hyperbolic cotangent of pi minus 4, where I've just multiplied the 4 in there, divided by 4. So notice that I have 2 times pi times hyperbolic cotangent minus 4 times pi times whatever. So that gives me negative 2 pi hyperbolic cotangent of pi minus pi squared times hyperbolic cosecant squared pi plus 4 divided by 4. And wait, we have a negative 2 on the right-hand side. And I think the equation I used for the 2 series, yeah, this negative 2 thing is actually pretty useful. I can just plug it into the equation in blue. Yeah, that's quite convenient. Oh, terribly sorry about that. So this means that the integral I equaled, the first series gave me pi times hyperbolic cotangent pi minus 1 by 2. I might as well expand this by 2 to make it, have the same denominators. Minus, no, a plus sign because I factored in the minus 2 already. So that is a minus 2 pi hyperbolic cotangent pi minus pi squared hyperbolic cosecant squared pi plus 4 divided by 4. I think I haven't messed anything up. There's some nice cancellation there, which is encouraging. Then I have negative 2 and a positive 4. That gives me 2. No! Okay, at least I recovered that factor of 2. Anyway, that was fun. So, what was I doing? Yes, of course. 2 minus 2 pi squared times hyperbolic cosecant squared pi divided by 4. So we can cancel out a factor of 2, which implies that the integral, the target integral, sorts out to 1/2 of 1 minus pi squared times the square of the hyperbolic cosecant of pi, which is a pretty awesome result. It is wonderful indeed, and I enjoyed everything apart from the labor of differentiating and applying the product and quotient rules. God damn, and I missed a factor of 2 there as well, so yeah. Anyway, that's it for today's video. I hope you enjoyed the video. Be sure to like and subscribe to support the channel. You can follow me on Instagram as well, link in the description below. And thank you. See you next time.